And here you can see that we go from 47 successful attacks to 18. So we have 1/3 of the attack surface. Obviously, we can keep working on these, right? We can keep fine-tuning the guardrails and the application to try and reduce these.
Building guardrails into your AI system to secure against an attack is one thing. Knowing whether they actually work is quite another. And this is where Donato, an AI security researcher at ReverseX, work really gets practical. ReverseX have open sourced a tool called Spikee, a testing framework that lets developers systematically attack their own AI systems to find weaknesses before the hackers do.
The first application I tested in 2023 had GPT 3.5 Turbo that was used to summarize emails that were coming from clients. That's the first thing I tested. So that's quite prehistoric for today's standards. But the problem we had back then, and I think this is still a problem, how do I test the security of my system from a cybersecurity point of view when it contains an LLM? Because clearly I need to prepare different prompt injection and attack payloads, and I need to see what's the impact of those and what are the permissions. And we were doing a lot of this manually. We were figuring it out in my team. And we started putting together all of these scripts into a tool that then we released at the beginning of this year as an open source tool, and just show it to people. It's open source. We're not selling this, but like it's a tool that's meant for people that need to test the applications that they're building with LLMs.
What makes Spikee powerful is that it automates what Donato's team used to do manually. Instead of crafting individual attack emails one by one, Spikee can generate hundreds of variations, trying different techniques in different languages, adding noise to bypass filters, and because it's open source, any developer can use it to stress test their AI systems before deployment.
Just very quickly show some of these. So for example, we help people create data sets that they can use for different types of attacks. So one of the data sets, for example, that we curated is the cybersecurity data set. So you can go in, the tool can do it for you, but the tool has got like common jailbreak and prompt injection patterns in all sorts of like different languages. For example, we saw that in the email before, new important instructions, but many other things. And then it's got this idea of what do you want the LLM to do. So there are all sorts of different kind of malicious outcomes. And so the tool allows you to very simply is a big word, but it allows you to basically generate a data set. This might be a little bit small, but it basically allows people to generate these data sets to target their applications. And then it can be run either manually or in a CI/CD pipeline against your application to see how vulnerable that particular application is to all of these well-known prompt injection patterns. And then it allows you to tune your guardrails. So maybe one thing that I will show an example of what it means to tune a guardrail and to test it and to test an application. So I have here a demo of this kind of webmail application. Is similar to what we saw before. And let's say I wanted to test it, not manually, but I wanted to test it against a lot of these potential prompt injection attacks. So I would basically, I'm just going to go high level. This is the stuff you can look at the commands later, but the idea is that you can create yourself a data set, not just with a few prompt injections, but with a lot of these different kind of jailbreaks that you can have in all sorts of like different languages. And here you see again some of the examples. And then you can, for example, this is a test, generate, emergency, developer, and so on. And then you can have instructions. For example, this is data exfiltration. So you want to test, can somebody steal information from this application with prompt injection? So you're basically setting up all of these, and the framework really helps you do that. And then it will generate for you, in this case, 61 emails that contain different types of attacks combined together. And then it allows you, I'm just going to probably skip forward a little bit because some of these details are less important, but basically what it's going to allow you to do, then you can take the data set, you can take your application, and you can test that. So of those, you can ask the question, of those 61 emails that contain well-known attacks, how many of these would be succeeding at stealing information from the application? So this obviously tells you quite badly that this is not a good application. There are no guardrails, and you see such a high success rate. And then what you can do is you can go in and enable some of these guardrails. So for example, let me just show that from here. So if I went in and, for example, I enabled a prompt injection guardrail, if I can get this video to go. So you see, I enable the Bedrock, AWS Bedrock Guardrails. I can rerun the same test, so the same data set, and now I can look at the attack success rate. So this allows me to measure how resilient, with toggling and enabling different guardrails that I showed you before, how resilient is it? What's the impact? And here you can see that we go from 47 successful attacks to 18. So we have 1/3 of the attack surface. Obviously, we can keep working on these, right? We can keep fine-tuning the guardrails in the application to try and reduce these.
Donato just showed us that enabling AWS's Bedrock Guardrails reduces successful attacks from 47 down to 18. And that sounds great until you realize that 18 still got through. Security isn't about perfection. It's about making attacks so expensive that most attackers give up before they succeed. But what if an attacker is willing to put in more effort, to pay more? That's what Donato's about to show us now.
And then one thing that I want to show, that the way we did this, then we can also ask, in Spikee, we can also ask, okay, now we have a baseline, we have a set of guardrails. How hard would it be, or what's the effort for an attacker to break this guardrail? Because I think this is a fundamental question for all of the security thinking that we do. And here I show one of the attacks in Spikee, which is called best of n. So you can do basically the same attack as before, but then you say, for each of the 61 emails that I have in this data set, I want you to try 30 iterations of this type of attack. And this is just an attack that uses, adds noise to the text to confuse the guardrail so that it doesn't recognize the attack as the email as malicious anymore. So obviously, if I run this, you will see that we have 61 emails, but we have 1,800 potential emails that we're sending, because we are, again, modifying and adding noise to see if we can bypass that particular guardrail. And you can see how much traffic is actually generated here. Now, obviously, this is more effort, but at the end of this, it will allow you to measure what's required by an attacker to break that guardrail. And in this particular case, with this effort, we see that from 18 successes, we go to 26 successes. So we have almost 2/3 more successful attacks. And so this is a way of using a framework like Spikee to test how resilient my guardrails are, and then to fine-tune them so that if somebody comes in and tries to do this, it's actually very hard for them to succeed. In the current release of Spikee that's public, we have best of n that you saw, anti-spotlighting. That's one of our attacks that works very well against prompt engineering. We've got prompt decomposition and random suffix search. And so these have got all, they target different types of guardrails, but in probably by the end of December, we're going to add more attacks. We have 4 attacks that we've been using at Reversec, like for our clients in the past few months. It's pretty new for everyone. I mean, as I always tell our clients, it's actually new for us as well.